All right, good morning, everyone. My name is Elena. I'm one of the teaching assistants in the data analytics program. Today, I'm going to cover the logistic regression, linear regression, and naive Bayes method. So, here is today's agenda. So we're going to do linear regression, and I'm going to show you how to build the model in R, the data pre-processing, and how to evaluate the model, and how to do the minimal adequate model, and explain you what it is. We're also going to do the logistic regression, and we also do the naive Bayes method. But as a bonus, for people who are attending this presentation, or at least watching the recording, I'll show you how to do the RAC curve and the effect plots. This topic is not in the exercise document that you have in the classroom. So that's a bonus. That's what it is. Now, let's continue. Here is a data set that we're going to use today for the purpose of this demo. And the topic in the data is a low birth weight. So we have the ID of an individual, and we have a variable that tracks if an individual was, if a baby was born underweight, and underweight means weight less than 2,500 grams, and we have a variable that's mother's age, the mother's weight at the last period, mother's race, and whether mother is smoking during the pregnancy, and the history of premature labor, and so on. And another variable at the end, if you see, it's a birth weight. So I'll show you what we're going to do. We're going to use the same data set for logistic regression and for linear regression. When we do the linear regression, we're going to predict the birth weight. And when we do the logistic regression in naive Bayes, we're going to predict if the baby is underweight. All right. And this web page is where you can read more about this data set. Now let's continue. Okay, this is very important step. First, we do the data pre-processing, but after that, we need to divide our data into a training set and a test set. The reason is we want to avoid the model overfitting. We don't want to overfit our model to the training data. So what we do is we split the data into the training and test. We use our training set to build the model, and we use the test set to evaluate the model. And we want to see approximately the same accuracy when we compare the accuracy on the test set with accuracy on the training set, right? And the first command that you see here is that set seed. You can put any number you like in there, but the purpose is you want your result to be reproducible. So in other words, if I start doing my homework today and I have to continue tomorrow, I should be able to pick up from where I stopped. I should be able to get the same result. Now let's continue. Here is a brief overview of the linear regression method. The method works well when your dependent variable is continuous, and when you have a linear relationship between the dependent variable and the independent variables. So here is basically the formula. You have alpha. This is an intercept. So that's basically what happens when all of these coefficients are 0. x1 through xn are our independent variable, also called predictors, and each variable has a coefficient next to it, and epsilon is an error. So what does the coefficient mean? It means that if I increase the x by 1 unit, if I increase the x here, x1 for instance, by 1 unit, it's an increase in y, assuming that the remaining variables are constant. So beta 1 is an increase in y when x1 is increased by 1, right? Now, The method further assumes that there are no linear relationship among the independent variables. In R, we're going to use lm function to run the method, and the method takes the following input parameters, and I'll demonstrate. So here it is. We're taking our formula, and a formula expresses the relationship between the dependent variable and the delimited list of independent variables. The delimiter is a plus. Alternatively, you can use a wildcard, .wildcard. The linear regression and logistic regression method, as well as naive Bayes, support this. Some methods, as you may see later in the course, they do not support the wildcard dot, and you have to physically spell out the names of the variables. And the data is going to be the name of your training data set, right? And then you can run the $ln. That's a command you run to learn more about the method. This is a help command, right? So now what I'll do is I'm going to physically go in and run the method on the data. I'm going to go ahead and share my screen. So remember, my data set, it tracks the body weight, right? It's a birth weight. It's a weight of the infant at birth. So we're going to run the linear regression method to predict the infant's weight at birth. What we have to do to start with is we need to load our data set, and we're going to preview our data set. I have a folder called datasets, and in that folder I have this data, lowbodyweight.csv, right? So I'm going to run my first command to set the working directory. Remember, the working directory is a folder where R attempts to read my data file. Now here I'm reading my file into the variable called low body weight, and when I do that, here I'm adding a data frame to my environment, right? Here is basically I want to preview my data. I check the dimension, I check the head command. It shows me the first six data rows, right? So here I've got the ID, and I've got the low variable. It tracks if the individual's birth weight is too low. And again, low means below the 2,500 grams. And this is a mother's age, right? And mother's race, and whether the mother is smoking, and so on. So now, the first thing, well, I want to do the summary command, of course. There is one variable in here that is skewed. And for the linear regression method, we want to remove the skewed variable if possible. So it's this one. If I run, I can run the table command on this one just to show you what I'm talking about. Table, right? If I put this here, see this? I have several options here. I can either combine these values, 2, 3, 4, and 6, right? I can combine them. Alternatively, I can just not use this variable because it's skewed, right? So now let's do data pre-processing. Here, I decided to remove the ID because it's a unique identifier. It does not really help me find the infant's birth weight. So I'll just run this. I remove it. Now, this variable, I want to remove it because in this specific problem, I'm predicting the weight. I don't want to predict whether a baby is underweight, right? So I'm going to remove that for right now. And this is a skewed variable. I want to remove it. My next step is to check if my data has the missing values, right? So this is how you do it. You can check the column sums, and this is NA. Is NA returns true, right? So basically what this here part does is it's going to build a matrix. This matrix, oh, I forgot to put the closing parenthesis. This matrix is going to return, right, if the value is missing. So see that? That's false. And when I do the column sums, it should show me 0. So this data set, the specific data set, has no missing values. But this is very important. You always want to check. Now, I'm going to do some data pre-processing. If you read the dataset description, the values of the rays are here, right? These 3. The values of the smokes or not are here, these 2. So those are actually the factors, right? So here it is. That's a data set right here. And it's showing me here. See this? This is a data set description. And right here, this is a value. So I want to recode it, right? I want to code them the way they are in the dataset description. So that's basically what I'm doing here. Factor will convert it to the factor because see how it's loaded? It's loaded as 0, 1. And levels, it's a current value, right? 1 through 3. And this is labels, right? So here are the levels, 1 to 3, and I want to show them as this. Labels is the way I want to display them. So take a look at this, right? So I just converted it to the factor, and I want to convert this one as well, right? So here again, I'm showing you the summary, right? See this? I converted it to the factor and showing you the summary, just for the illustration purposes that this is skewed, right? So now what I'll do is, oh, here it is, the PTL. Now we're going to convert it like this. So if this is greater than 1, then it's going to be false. And if it's equal to 1, then it's going to be yes, right? So if you look at it, this variable, oh, that's variable, it tracks the preterm labor. This is tracked as a preterm if the mother has a history of the preterm labor. So this is what I'm doing. It's actually the variable is skewed, right? So what I want to do is I want to combine the 3. So here is the number of preterm births. I want to treat it as yes if it's 1 or higher, and no if it's 0, right? This is what I want to do. I'm just showing you 2 different approaches. In the approach above, I eliminated the skewed variable. Here, instead of eliminating it, I just want to combine these 3 values. That's another option, right? So if you notice in your homework assignment, you are asked to eliminate 3 or 4 variables. It's because of the skewness. But you have an option to combine the value. Just keep this in mind, right? So I ran this. Right, no, I have not run this. Let's run it again. Let's run it. Here we go. Now here, this variable, if you notice here, right, in the description, I want to do this. It's a presence of irregularity, so I want to do this as yes, no. And here as well, right? So here, basically what I'm doing is that I want to match it the dataset description. Next step is I want to set seed. And the reason we do it is because I want my result to be reproducible. If I have to rerun this script tomorrow, I want to get the same result that I have today. The next step is to divide the data into training and test set. And we do that because I don't want my model to overfeed the training data. I want to build the model using the training data, and I want to evaluate the model on the test data. So here, let's run this. So over here, if I look at it, I should see the training data, and I'm doing 70%, and I should see the test data as well, right? Oh, I didn't run it. I didn't run it right. There we go. So now I see it. No? Okay, let me run it. Here it is. Now, next step, I'm going to build my model, and I'm going to do the results interpretation. Now, here, LM, right? Over here is very important. This is the name of my dependent variable, which is the body weight. It's the weight of an infant. Here, tilde, and here is the formula. This is a wildcard, right? So the nice thing about linear regression is that it allows you to use the wildcard dot. You don't need to type the names of the independent variable here. So dot is going to make the remaining variables as independent. So here, see this, the body weight is a dependent, and I want to use everything remaining as body weight is a dependent, and here is independent, right? So now what I'll do is I'm going to run my model to output the result here. I can use the print command, or I can simply type model. Here, what I see is I see call. Call is a command we used to build the model. This is a formula, and this is a data set. Alternatively, I could create a separate variable called formula and set it to this piece, and then just put formula. The reason I didn't do it because I want this to show an actual formula. I want to see this. Here are my coefficients and an intercept, right? So intercept is basically the value of the weight of the body weight when all of these are 0. Well, of course, they're not going to be 0, but basically that's what it is, right? Because if you look at it, assume that you had only one independent variable. That would have been a line, and the coefficient would have been a line slope, right? So slope is a rise over run. So that's a change in the dependent variable if we increase the dependent variable by 1 unit, right? That's what it means. And when the coefficients are negative, right, it means that this is a drop in weight, right, if the race is other. Now, I want to point out here something, that race is a categorical variable. So what R does is it's going to treat the categorical variable as a set of dummy variables. In this case, race has 3 values. So it's going to create 2 variables, right? It's going to create 2 variables and use the third value as a reference, right? So basically, if race is neither of these 2, right, then it's going to treat the coefficient for race as 0, right? So if race is neither white nor black, then it's going to subtract this number from the weight. Smoking, the values are yes and no, right? So if the value is known, it's treated as 0. The intercept, the coefficient for the smoke, is treated as 0. And if mother is smoking, it's going to subtract this number from the baby's weight, right? If we analyze the other variable, other coefficients in a similar way, but the categorical variables are very important because R will create a set of dummy variables. This is a case for linear regression and also for the logistic regression, right? So now this is more. I can do the summary. The summary command shows me much more. Here, the residuals, right? So that's a difference between actual values and predicted values. And it's going to show me the maximum residuals, medium residuals, and the median. So this is a distribution of the residuals, so to speak. Here, I get the estimated coefficient. I also have the t-values and the p-values. So for the 95% confidence interval, if the p-value is below 0.05, then my coefficient is statistically significant. Here, apparently, the intercept is significant, and the race seems to be significant, and this is also the statistically significant, right? So LWT is an infant weight at the last period. And here, if you look at the dataset description, so HT is a history of the hypertension, right? The blood pressure issues. Apparently, the blood pressure history of the hypertension, yes, has an impact on the baby's low birth weight, right? Smoking has a little impact, right? And this variable here is almost none. Here are the other measures. This is an overall p-value, right? So it's a p-value for the null hypothesis test when all coefficients are 0 simultaneously. See this? You notice this intercept, there are 3 dots, the 3 asterisks rather, so this intercept is very statistically significant. And I want to show you something in the slides. What I did was I kind of like summarized it for you, right? So the relationship between dependent and independent variables is represented as a hyperplane, and you have the question in your homework assignment. So the relationship is represented as a hyperplane, where you have the coefficient, right? You just saw it in the output. This is your beta 1, beta 2. So this is actually in this column, right? And if you look at it here, it just basically telling you that the method assumes that you don't have the linear relationship between the independent variables, right? So LM is the function I used. LM, actually. See this? I have a typo in here. I'm going to give you a copy of the slides after class, all right? You have a recording and a copy of the slides. Now, here I'm summarizing the output for you. So call is a command we ran, and here residuals is the deviance residuals, and then coefficients in the change in the birth weight if I change my independent variable by 1 with the assumption that the rest of the variable are constant. And here just keep in mind this, that each categorical variables, if you've got n levels, there are going to be n-1 dummy variables. Now here what I'm doing is, this is a linear regression evaluation criteria. We're going to look at the alkaline information criteria. So this is also called the goodness of fit. The lower values are better, and I'll show you. P-value, if it's less than 0.05, it means that our coefficient is significant, as I just showed you. And also, the t-statistics, it should be above 1.96, just to obtain this value here, below 0.75. Also, what you need to keep in mind that your R-squared gets bigger when you increase the number of variables. But this is a preferred number, 0.7 or above. You also got adjusted R-squared, and you've got the standard error. It's a measure of variation of observation around the regression line, right? So if you notice here, and we're going to do this plot, the plot is doing observed values versus prediction, and I have a 45-degree line. If the point lies on a 45-degree line, it means that the observed value, right, observed actual body weight is equal to the predicted body weight, birth weight rather, right? It's a weight of the infant. Now, Okay, so let's continue running. I did not run all the commands. Here is the rest of the script, right? So here is how you view just the coefficients. If you're doing the result interpretation, you want to discuss just the coefficients. And I put more than one way. You can write this command, or you can just do this model coefficient. Because what I want you to see is that this is actually a list variable. And if you like, what you can do is, when you run the names command, right, remember names for the data frame, it gives you the list of variables. But here, it gives you the list of additional components of the output. So if you want to do that for your, not the exercise, but for your assignment, if you want to further explore, you can look at these portions, right? Now here, this is the residuals sections, and alternatively you can do this. It's a residual for each observation. Now, something else that I did not do is here I want to do predictions on my test set. Remember, I'm running the model on a training set, but I have to do prediction for the, I have to do this for the test set, right? And I'm going to do my plot here. This is an observed versus predicted plot. The command upline will add the 45-degree line. So this is an intercept. I want the line to start with a 0.00, and here is the slope. This is going to give me the 45-degree line, and if the point lies on this line, it means that observed equal to predicted, right? Now what I want to do is I want to build the reduced model, because you want to make sure that you have only the most significant variables remaining, right? So here I'm going to build the model 2 step, and the direction is backward. So let's do that. What it's going to do is, it's going to remove the least significant, one least significant variable at a time, and it will continue until there is no change. So let's go back, start here. See this, the AUC is going to pick up the age, right? Because the age has the lowest AUC, right? Take a look at it. It has age. I have age at the top. And now, if I scroll down, age is gone. Now we're going to remove PTL, right? And we keep going until we have nothing else to remove. This is an intercept. So these are the remaining variables. And what I could do here, I can do my summary command, and I can see the coefficients for my new model, right? So these are the coefficients for my new model, and I can interpret it again. I'm leaving only the significant values, and then you want to look at the p-values, and you also want to look at your F statistics, and so on, the R squared, right? And 6 over here, this is a number of variables that you have, right? Well, number of variables plus intercept. 1, 2, 3. Oh, actually, no, intercept does not count. It's just a number of variables. Okay? So now what we're going to do, so this is your linear regression, right? Another thing that I want to point out, that in your exercise, you have a question: how are you going to predict the value for the new instance? In this case, my new instance is a new baby, and I want to predict the birth weight of my new baby, assuming that I know all the values of all independent variables, right? So if I'm right here, I know all of these independent variables, and I want to predict my birth weight. So this is what you do. Here, this is an expression over the hyperplane, right? So we're going to know what an intercept is. Oops. We know what an intercept is, right? So we know what our coefficients are, right? We plug it in. We know it from the model here. And we know the values of the independent variables. So why don't we substitute them in this formula here? If I substitute it, I get my y. Y is the baby's weight at birth. Very simple, right? You just substitute. So this is what you get for attending this lecture and or at least for watching it, right? You get your questions answered, right? So now this is linear regression, and we use it when you have the linear relationship, or you think you have a linear relationship, and also you use it when the dependent variable has to be continuous. So continuous means that the number of valid values is not limited, right? And you don't know the number of valid values ahead of time, and it's a number, such as weight, right? Weight is a number, and there is no set of limited, so it could be 0.5, 0.55, right? And it's a continuous number. Now, let's look at the different problem here. Now I want to predict if my baby is born underweight. What is the likelihood that my baby will be born underweight? And I'm going to use two methods for this. I'm going to use the logistic regression, and I'm going to show you naive Bayes as well. Now, here it is. I'm going to start the data pre-processing all over because it could be slightly different, because this is a different method. Okay? So what I'm doing here, I'm going to load my data once again, and I'm going to do the load, right? Now I'm going to check the dimensions, and once again you want to preview how the data looks like. Right now I will keep this variable, right? Because low means if the body weight if the birth weight is below 2500, actually, see, this low is rather, if 0, it means the baby is born normal weight, actually. I think, let's look at this description once again. See this? Low, right? If 1, it means the birth weight is below 2500. Or in other words, the baby is underweight. And here, it means the baby is born normal. So this is what we want to focus on right now. That's why I'm going to remove the birth weight, right? Because we don't want this to interfere with our results. Similarly, I want to remove this skewed variable, and I also want to remove the unique identifier because it doesn't really add the value to analysis. Let me do run. Here I have to check if there are any missing values. If there are none, then I don't need to worry about anything. Here I'm doing the same recording that I did for the linear regression method. Right? I'm doing the same thing. And here I'm just showing you what this variable happens here. Instead of dropping this variable, I want to combine these values. This is another approach. And same thing in your homework assignment. You have the skewed variable, right? So I told you explicitly to remove it. So here it is. And this is just, oops. Oh, I should delete it because I removed this variable. I removed this variable from... Initially, I thought about combining the values, but then I said, no, I'm going to remove it just to show you that you can handle it in more than one way. But you don't want to keep extra variables. It's sensitive to the number of variables as well. I forgot to show you something very important because before we run the method, we have to understand what it does. So you want to use this method when the dependent variable is binary, 0 or 1, and this is a GLM is a function that you use to run this method in R, and the GLM stands for Generalized Linear Model, and this is your best friend. You want to run the help command always to check what the method takes as an input parameters. Formula is an expression. It expresses the relationship between dependent variables, and you've got the list of independent variables delimited by the plus. Alternatively, you may use this wildcard dot, and also data is your training set that you're using to train the model, and family is an error function. In this case, you have to use binomial because the output is 0 and 1, right? So you have to use binomial. Now here I'm summarizing the components of the output. So let's run this to see the output. But before we do, here keep in mind that you have to set seed because we want our result to be reproducible, right? Your homework sometimes cannot be done in one sitting. So when I do this, when I start today, and when I continue tomorrow, I should be able to run my script and get the same result. So I'm going to do this, and I pick the number. You may pick anything you like. Here, I'm dividing the data into training set and test set. So in your homework, you want to explain that you do that because to prevent the overfitting, right? You want to reevaluate the model on test set, right? Now what I'm doing is I'm running my GLM, right? I'm running GLM function, and I'm going to store my results in a variable called model. Similarly to the linear regression model, the output is going to show you the coefficients and an intercept. Let me run this quickly. So here, this is a command I use to run the method. And again, I could create a separate variable called formula. Well, the reason I didn't do it because I want to explicitly see my formula here. There is more than one approach to do this, but I did it this way in the demo. I want to do it differently. Here, the summary command is going to show you the p-values in addition to the coefficient, right? Here it is. I see the deviance residuals, and I also see these p-values, right? And the dot and the asterisks shows me which variables are statistically significant. Similar to linear regression, it's looking at converts the categorical variable to a set of dummy variables. So if the variable has 3 values, it's going to be 2 dummy variables. And instead of the actual value of the weight, this is a log of odds. It increases the load of odds that my baby is going to be born underweight. So see here, if the mother is smoking, right, this is an increase in the log of odds that my baby is going to be born underweight. Here is an age, right? So if the mother gets older, as the mother gets older by 1 year, this is a decrease in the log of odds that the baby will be born underweight. And same thing, you've got the p-values, and you've got all of this here, right? AUC, and this is a number of method iterations. So you have all of this information, and if you go here, and after this class, I'm gonna pause the recording and I'm gonna pause the slides as well. But what I did here, I explained it to you. So the residual, this is a model fit. it's a difference between the predicted log, right, the likelihood of an outcome, and the actual probability of an outcome, right? So now the deviance residuals, as I show you the distribution, right? The null deviance, this is also called the chi-squared value. So this is a deviance when all independent variables are 0. So in other words, you have only one intercept. So null deviance is a deviance when you have only one intercept. And here, right, residual deviance is a deviance when you have all independent variables are non-zero, right? And the goal, you want to minimize the sum of squared residual deviance. You want to minimize this, right? Now, here, I just wrote it out for you, the p-values, and these are the coefficient. Again, it's a change in the log of odds that the baby's weight is going to be below 2,500 grams. And each categorical variable with n values is going to be n minus 1 dummy variables. And the intercept is a base log of odds. So this is basically when all coefficients are 0, right? Positive coefficient is an increase in the risk, and negative coefficient is a decrease in the risk that baby is underweight. And you can see here that which two variables are the most significant, right? And also LWT, right? These three variables are the most significant, right? What I did is, see, I put this here so that, right, I made a correction, so that way you have a correction when you receive the copy of the slides after class. So now let's go back to our RStudio, and I'm going to show you more stuff. I'm going to minimize this. So here I've got the residuals. This is another way to show the residuals, and this is going to be the coefficients. That's an odd watch ratios. So if you were going to do the actual calculation, you have to get these coefficients, right? You have to take the exponential. Exponential is the opposite of the log. This is an alternative way. Now what I'll do is, I'm going to see how good is my actual model. Here, I'm still working on the training data, and I'm going to store the predictions in a variable called my prediction. And the predict function, it takes, this is a model, and by default, it's going to take the training data. And here, I'll show you what I'm talking about, but I want to predict the response. So I want to see if the individual is likely to give birth to the underweight baby or not. I don't want to see the percentages. I want to see the actual value. So this is what it's going to do. Now I'm going to run this, and I store the variable in my predictions, right? So now I want to print the confusion matrix, but actually before I do this, let me do this. Let's put this head. I want to show you what it's going to be. So see this, apparently the first 6 are 0, the first 6 observations in the training set. Notice that it doesn't have 5. It's because observation 5 may have fell in the test set, right? Now what I'll do is, I'm going to build my confusion matrix. Let me run this. Yes, I want to show you what I did here. I did something that it's not done in your exercise instructions, but in your assignment, you may find it helpful to do it because it's going to be the output is going to be more readable. So look here, table. My prediction is the predicted value. And here, training data, LOW, this is the actual value. There is another input parameter. This will put the labels to the confusion matrix. See this? I put the labels so that columns are actual values and the rows are predicted values. Okay? I wanted to put labels to make it clear, or otherwise I always have to second guess where am I predicted, where am I actual. So this will help you read. It improves the readability. Now, here the way you interpret it is that I predicted that my baby is not going to be underweight, and it's actually not underweight. Or I predicted that the baby is going to be underweight and the baby is underweight. Or I predicted underweight and the baby is not, so that's a false positive, right? I predicted that my baby is not going to be underweight, but my baby is. False negative. Notice that the numbers of a diagonal, right, these two numbers mean where my predicted value matches my actual value. So, to calculate the classification accuracy, I have to take my numbers on the diagonal and divide the total sum of numbers in the confusion matrix. The total sum of numbers is a number of instances in my training set in this case. So here, I'm just showing you how to do it programmatically, right? This will programmatically calculate this is the accuracy on my training set, and this is the error on the training set, right? So what I'm doing here, this is a predict. Well, alternatively, instead of putting predict here, I can put my prediction variable. I could put my prediction to make it more readable. And here, this is the training, right? This is the actual value. And I'm just trying to see if it's not equal to, right? So this is a way to do this error programmatically. If you wanted to do the calculation, you would have to do this 31 plus 6, which is 37. You would have to divide by the total. Now what we're going to do is we're going to predict what's going to happen on the test data, right? And I thought I had it here, but maybe I did not. So let's do this. I want to show you, just for the demo purposes, I want to show you the difference here. Now here, actually, let's just do this. Let's just do this here. Quickly run this. I want to show you what's the differences between row and response. When I do row, it's going to give me the percentages. Oops. I think I misspelled it. But anyways, when I do row, it's going to give me the percentages. Right? Well, I misspelled it. But anyhow, what I wanted to tell you is that in this case, I'm interested in predicting the response. I'm interested in predicting the response here. I'm not interested to see the percentages or anything else. Oh, actually, I lied. The percentages are for naive Bayes method. It's not for the logistic regression. Okay? The percentages are for the naive Bayes. But here, what I'm saying is that you want to do the predict, I want to do the response. I want to see this, right? And you have to round it because it does show the percentage for the class value 1. So I have to round this. And I'm going to store it in my predictions. I'm going to store it in my predictions. And here is a confusion matrix for my test data, right? So this is important because this is a test data. And I want to have the accuracy for the test data to be approximately equal, because if the gap is big, then probably more likely my model overfit the training data. So now let's do this. Well, this was fine. See this? I had 73 for the training data, now I have 70. This is fine. But if I had 90% for my training data and 70% for the set data, I have a problem. It means that my model overfits the training data, right? We want it to be approximately same. And here I'm running the predict command. This is the error, right? And if you notice that these two numbers add up to 100. Right? Now what we're going to do is we're going to build a RAG curve. What you need to do is, to do this, you would have to install this package. It needs to be done under only one. And the RAG curve is the false positive rate over true positive. It tells you how good actually the model is. How good is my model? And you want the curve to be closer to 1, as close as possible to 1. Now here, what I'm doing is, I'm running the prediction command, and I'm going to store it in this variable. But before I do this, yes, very important, I installed this package already, but I still cannot use it because I did not put my package in memory. I have to load this package in memory. Something I want to show you here. Usually, you'll see this message in red. It depends on your RStudio configuration, on the options on how you configure these fonts here, right? It depends. If I open the global option, I have option to configure my fonts, right? So see this font and this theme. Depending on the theme you choose, all messages may show in red. If you see a message in red, it does not necessarily mean that your message is an error. It may not be an error. The message could be informative, or it could be a warning. Perhaps my package could depend on something else in another package. Well, and maybe another package does not exist, but then if I get a warning, it means that the issue could affect only specific functions. But if I'm not using the function in question, then I'm still good, right? Or this one, this is just the informative message. It tells me that it also loaded this package because this package that I just loaded, it depends on a gplot package. So it loaded the dependency, right? And it's showing me here, this function apparently appears in both packages. And since I just loaded this package, it's just going to take priority over this function in a start. But we don't care about it at the moment because we're not using this function, right? So sometimes two packages may have more than the same function. And when I loaded this package here, if I call this function, it will use this function in my package that I just loaded, if I was going to call. So this is what this message says. This is not an error. Now, what I could do, I'm going to build my performance curve, true positive over false positive, and I'm going to do the plot, right? Oops, it takes a while. Oh, no, see this? The error, because I did not run this command. See this is an error message. It's not finding this variable. It's because I actually had to hit run. There we go. And now I'm going to do my plot. But look, we want to make sure, we want to see how far away this line is from the 45-degree line. So I have to plot my 45-degree line. And these two parameters just tell me the line width and the line color. This is a line type rather, right? So this is cosmetics. And here, this is just the color code. So the curve, the area goes from 0.5 to 1. If it's close to 0.5, it means my model is not as reliable. Now, here, you can do the residuals plot. This is another way to do this. And basically, one way to do this plot is just by typing, just by using the plot function, right? But here, this is an alternative way, and you may notice in your classroom there are some pictures, and all of these graphics were generated in R. So there we go. This will do this values here, and now I want to plot the lines, right? The actual values, and this is going to be the horizontal line, right? So basically, in other words, what I'm doing here, nothing but just showing you that there is more than one way to achieve the same plot, right? There is more than one way to achieve the same plot. And you basically are looking at the distance between this line, right, and this, yeah. Now what we'll do, this is something else, and we want to look at the effect that each individual variable has on a model, right? Each individual effect of each individual variable. But I'm gonna give you an idea. When you writing your assignment 1, this is something to look at. It's going to add value to your paper, right? You would need to install this package, and this is a library, effects. I'm gonna run this. Library. Remember, library load this package in memory, and here is my plot. Take a look at this. Now what I need to do is I can zoom in, and it's gonna give me every variable, right? This is basically show me how the change in weight has an impact on the change in age. This is a change in age, how it has an impact on a variable, right? And here, if you notice that these are the values of my categorical variable, and here the lines in red, there are the confidence interval. So 95% confident interval, so it's a 95% chance that the value will fall between these two, right? So if you go and look at your coefficients, it will make sense. It will make sense when you go back and to look at your output, right here, right? This is a logistic regression coefficient. See this? So if somebody is a smoker, it's plus 0.5. And now if I'm going here, same, see this? I want to look at my effects. See this? This unhit this line. Yeah. So it's approximately something like this, right? It's showing me the impact of the variable. It's showing me the impact of the value. It's showing me the effect. What's going to happen to the... it's showing me what's going to happen to the probability, right? Or log of odds, likelihood of odds, that my baby will be born underweight. And actually, I have to look at the exponential. I have to look at the exponential, not just at the ratio. Remember earlier, I ran this exponential. Or I thought I ran it. I'll find it. Over here. Didn't we run this thing here? So this is the exponential. See this? You have to look at these coefficients here too, right? When you're doing your results interpretation, you want to look at this as well, and you want to look at the you want to look at the result output as well, right? You want to look at this, and you want to look at your model, the summary, output of the summary command. But what you could do here is read more about the effects, and this will add value. Now here, I'm just doing the reduced model. That's something that you would probably be interested to do as well. I'm using the step function, and here is the summary. There we go. So that continues removing one variable at a time until there is no change in AIC. Right. So that's similar. This is very similar to what you have seen in a linear regression. And here I'm just trying to run the model on a test set. This is a reduced model. I'm just trying to do that here. And I'm trying to see the accuracy. It went up to 72%, right? So now, naive Bayes method. You also use this method when you have, well, in this case, in our example, the dependent variable, it has two values, right? 0 and 1. We're going to use the same variable to predict the probability, or to predict the chance, rather, that my baby will be born underweight, right? So this is a package that I need to install. I'm installing it only once, right? I'm installing this package only once, but I have to load this in memory when I start the session, because even though I have the package installed on my disk, I still cannot use it. I can use only what's in my memory, right? So I already have it installed, so I'm going to run the library command. And this is another command. You have to use it for the discretization. Well, the method will run when the independent variables are numeric, but it's a little harder to interpret the results. For the dependent variable, it must be categorical, right? Otherwise, the method won't work as expected. So I'm going to load the rule package, but now let's go back to the slides to see my summary. And see again, I see this little warning or little notification. Don't be scared of it, it's fine. So now let's go here and yeah, so here I summarized it, right? I put a nice summary of the confusion matrix for you, and after class you're gonna have this, you're gonna have all of these effects here, right? You're gonna have this, and I explained it, 95% confidence interval and so on. Now, naive Bayes method. This is supervised classification method, right? And the reason it's called naive because there is an assumption that all my independent variables are independent. There is no dependency, right? So, for instance, if the mother is smoking, it does not have anything to do if the mother has the preterm labor. It's independent. The method estimates the class probability, and also each independent variable has an equal weight on a dependent variable. As you see later on in the course, for instance, neural network, it will assign the weights to each independent variable. But this method does not. It assumes that all variables are equal. So if you have to do some data pre-processing, you better do it before. Now, I'll show you what I mean exactly. The class probability is going to be the product of, that's something called a priori probability, and I'll explain it to you, right? And we have to look at also the conditional probability. I'll look at it. We'll look at it, right? Let's go back here, and first we're going to run the data pre-processing. Let's close this. Let's go in here. I'm going to reload my data again because I might decide to do a slightly different data preprocessing, and in fact, I will do it. Now, I'm gonna preview my data, right? Here, I want to remove the ID because it's a unique identifier, right? And here, I want to remove the weight because I'm not interested in the weight. Now, here, this is variable is cubed, so I just decided to keep removing it. Here, I'm checking for missing values, and I don't have any. Now, here, this we're going to make the dependent variable a factor. So, actually, if you in fact look at this, this is a dependent variable, right? This is a dependent variable. So if you look at it here, the values are 0 and 1. Since we don't use the discretization here because although the variable is integer, it has a predefined number of values. The values are 0 and 1. So if the number of values is discrete, to convert this to categorical, you have to use the factor run. And here, the same thing. I'm going to record these variables. This is the same thing. Now, here, I'm going to, well, I'm just running the summary command just to illustrate why I want to combine these three values. Because this is skewed, right? This is skewed. And another issue is that, see this, I'll have only one observation of the class 3. Think about what happens if this observation falls into the training set. I don't have any observation, right, with value 3 in the test set, or vice versa, right? So here it's going to be a problem, right? So now let's do this here, and here, and here. Now we're going to do discretization. Remember that we have to pick the good value for the number of intervals. But also, if you run the histogram command, you're going to see that age is a bit skewed as well. Oops. Oops. I made a mistake. It's because I have to put I have to put the data frame name, right? And then I have to put this $sign, and I have to put this variable name. See this? This is a histogram. This is skewed, right? So I cannot use the equal width interval, but let me see if I can use the equal frequency. And I just picked 6. Well, maybe because I want all of this at the end to fall in the same interval. This is what I want, I think. Right, so let me see. And something similar I did for this. This is a baby weight at the last mother's period. There we go. Now what I'm going to do, guess what? We have to set the seed because I want my results to be reproducible. And I'm going to divide my data into training and test set because I want to avoid overfitting my model. And here I'm going to build my model, right, on the training data. I'm going to put display the output, and I'll show you what's going to happen here. If I scroll up, or let's just do this here, this here is a percentage of instances that have a value 0. Now, another problem that I have here is that the distribution for the variable, for the class variable, is also skewed. So when you take another course, the next course, they will show you how to deal with this. But for the purpose of this class, let's just leave it as is. So a priori probabilities are also known as prior probabilities. So my data set, this is a percentage of babies who are born normal, and this is a percentage of babies who are born underweight, right? So this is a chance in general that my baby will be born underweight. This is in general. Here are the conditional probabilities. So what I'm saying here is that assuming that my baby is not born underweight, right? This is a probability that my age will fall into this range. Assuming that my weight is 1, assuming that the baby is born underweight, this is a probability that the weight, that the age will fall into this range. And similar, I can look at this, right? So, in order to predict the probability predict the chance that my baby will be born underweight, what you need to do is, you need to look at this. Oops, you need to look at here, like for example, what's the probability that my baby is born underweight, right? I have to look at which age range is my independent variable falls into. So for example, suppose that mother is between 21 and 24 years old. So I have to take this number because I'm looking at the probability of 1, right? I have to take this number. Then I keep going for each independent variable. Suppose that this weight falls into here, right? So I have to take this one, and I multiply all of these probabilities, and I have to divide by this prior probability. So I have to take the product of conditional probabilities for each value of the independent variable and divide it by a priori, prior probability. This is how you get the new instance. And this is what these tables are. Because alternatively, I can predict the probabilities that my baby is not born underweight, can I? Yes, of course. Right? All right. So this is your result interpretation. Now, what we'll do, we already built the model. And here, this is what I'm trying to show you here. The a priori portion of the output is the proportion. This is nothing but the proportion. Remember this, the table command gives you the frequency count, right? The table command gives you the frequency count. But if you put the output of the table command inside this command, you get the proportions. So if you run this now, you get the same numbers as in the a priori section of the output. I wanted to show you that. Now, here where the row comes from. You have two options here to see the predicted value. So we're going to predict value right now on the train data. When you put the row, it's going to show you the percentages. Here are my percentages for every single instance in a test set. I'm going to see the chance, the probabilities that an individual is not overweight, and the probabilities that an individual is overweight, right? So this is what's going to happen, right? Alternatively, I can do this class. Now, you might be wondering why I don't see that many instances here. Right? It's because what I'm looking at, this is just a training set. Oh, I'm sorry, test set. Oh, this is a training set, rather. I'm still looking at the training set, my bad, right? This is a training. So now I'm going to look at the class. So this is a class, right? So if you look at it, for example, here is 0. It means that when I scroll up over here, see this? The probability here is higher than the probability of 1. It picks up the greatest probability. Here will be 0 as well. Here will be 0. 0, 0. Well, it's because our distribution for this variable is skewed, so that's why. Now, what else I could do here? I want to do the confusion matrix. I could store this in a variable. It would have been probably better if I did that. When you build the confusion matrix, you want to choose class. And here I put the labels. This is to make it more readable. I put, oops, because I did not create something. I see. It's because what I have to do here, I have to run it. I have to do this. Did I run this thing here? Okay, so this is, let's rerun it. Let's rerun it this here. Okay, I'm gonna rerun this. Okay, I got a warning. That's okay. I got a warning because I already discretized that variable. But I think I got my error because I forgot to convert this one. I forgot to run everything. I already discretized it. I'm good. This is an error message, but we can ignore. It's because I already applied the discretization. So I'm running this again. Now, what I'll do is I just showed you how to do that. And here, I'm just want to, oops. Anyhow, what I want to do is, oh, look at this, that's why. This is a typo. See this? I made a typo, that's why, but let's run this. It should work right now. There we go. So, now take a look at this. I have predicted versus actual, right? And you interpret it the same way, something similar as you were interpreting the logistic regression. I have 91 babies who were predicted born as normal weight, and they were born at normal weight, not underweight. And I predicted 8 born underweight, and they were born underweight. And here it shows you how to get the classification accuracy and how to get the error programmatically. Oh, that's a bit too low, but, well, you know. Let's do this on a test set. Run. Oh, here, this is basically showing you the difference between row and class. I'm doing it for the test set too. And here, I'm going to do the prediction. I'm going to do the confusion matrix, right? And I'm going to calculate this accuracy programmatically, right? So it's about 70%, and I'm going to get the error. Now, notice that it's even higher, a little bit higher than on the training set, but it's approximately equal. You want it to be close because you don't want the model to overfit or underfit the training data. Now, it's also possible to plot the ROC curve for naive base, but it's a little bit tricky because here, what I'll do, I do the predict here, right? But the problem is that this here, this is going to be numeric. This has to be numeric. But if I take a look at this. If I look at my predictions, right, what is this? Take a look at, my predictions, see this? It's a factor, right? Isn't it? It's a factor. I have to make it a number. But the problem is, if I convert this to number, it's gonna show me 1 and 0. Because it's gonna take, here 0, it means that the value is a first level. Here, if I have a 1, this is a value of the second level, right? So this is what it's doing here. So, just to trick it, I added -1. I'm subtracting a 1, and that will do it. Now, here, let's run this, run this, run this, and I just want to add the line, right? So you want this to be as far as possible from this line. Now, let's go back to our PowerPoint slides. Here, I'm just adding the explanation, how we do this, how to calculate the probability. You want to look at the a priori, and you want probability, and you want to look at the conditional probabilities, right? Here, I'm just showing you how to run the method. And remember the package, this is a package that you need to have to run this method. Here is a formula. This is my dependent variable, and here I put independent, but I'm using the wildcard character. And then I'm having this, I'm taking the training data to start with, right? And if you run this here, you can read the help page. And this is important. Your dependent variable must be categorical to use this method. Here, I'm just summarizing it for you, right? I'm just trying to write it down, so that's why you have written description and also the verbal. Here, I'm just going over what you can do to evaluate the model. This is just to evaluate the model, how you would do it about the predicting, the predicted values, and then the confusion matrix, and also plot the ROC curve. And now is the time for questions and answers. I love questions, right? I love questions. When nobody asks questions, Elena start asking questions. So let me go ahead and let me open up the chat. Yes, Sandy, go ahead.
Okay, can you hear me?
Yes, I can hear you.
Okay. Are you going to be providing the R script?
Yes, definitely 3 scripts. Not 1, but 3. Yes.
Good, because I found it confusing in following the fact when you would go back and you would reload the data in the current script, and I thought for for learning purposes, it would be better if you just had multiple scripts. So
That's what I did.
Take care of that.
Linear regression?
Well, linear regression and the
naive Bayes. Yeah, that's what I did.
naive Bayes and all that.
Yes, that's what I did. I found that easier to even to present. And what I did was, I named it, and the naming convention I use, I put the dataset name, and I put the method name, right? Linear regression. .r. Yeah, I'm using the naming convention just to help you. And the way I like to post things in a conference, I like to put it as a table, so that way it shows you what each file contains. Did you find this layout helpful? In the classroom, if you notice that, I put the files in a tabular format.
Oh, yes, I found that helpful.
Sure, yes. So this is...
Okay, go ahead.
Yeah, I was going to say just a little bit of HTML, but it's simple. So, yeah, I'll keep doing that in this layout. Because there's going to be a link to recording, that's one file. There's going to be the data file. I'll give you copies of the data set in case you want to follow along, so that's 2. The third file is the slides, and 3 more files for the script. So that's going to be like what? 6 links, right? So that's why, yeah. But I put it separately, yeah. But the reason I reloaded it is because different methods, the pre-processing is a little bit different. For example, I had to convert the variable to the categorical for the naive Bayes, right? And also, if you read the help page, it will tell you the necessary pre-processing steps. Yes. I hope I answered the question.
You did, and I find that listening to your lecture really helps in terms of workflow. With this type of problem, and this is the way your data looks like, then first you do this, then you do this, then you do this, then you do this. It's really good for the big picture.
Thank you. I'm glad I could help, yes. So I think John is going to be doing the next class on next class is going to be on decision trees, right? I think. Yeah. So it's in a couple weeks from now? Yes. Yes. And you may have read the announcement. I'm the Yelena who led the team of students, and we participated in a Watson Analytics global competition, and we tied the first place with another team in Canada. So you may have seen the announcement. That's me. I'm Yelena, the same Yelena.
Congrats, Yelena. We saw that announcement.
Thank you, thank you. So yeah, I think some of you may have worked with me in Data Extend, didn't you? You may.
Yes.
Have. Yes. So I'm the same Yelena. Yeah. So yeah.
Elena, in this linear regression method, LM method, uh, where do you see the prediction accuracy?
Oh.
In the coefficients and the residuals.
Oh. Yeah, you have to run this. You have to get the predictions. Basically, this is a little different because you have to look at the R squared. You have to look at the R squared, the difference between the actual value and predicted values. The evaluation metrics are completely different for the linear regression, right?
Yes.
So it is here, and you need to look here at the p-values, and you want to look at the R squared, and you want to look at the F statistics, right? And the higher is the better, actually. And you want to look at the standard error, right? So the standard error is at the bottom. It's in here at the it should be at the bottom here.
Yes.
Yeah. So you have to look at this section down there. Yeah, that's what you're doing. It's so different. Yeah.
Can you make that slide?
Oh yeah. Absolutely. Like this?
Yeah.
Oh, I could close this. Yeah. Or yeah, does it help?
Yeah. So in this one, can you? Okay. Where do you see?
Oh, I'm sorry.
Yeah. Where do you see the p-values on all those? F statistic. Okay.
Yes. So this is what you're gonna look at for your assignment. You see this, right? You have to look at this residual standard error. It's a measure of the variation of observation around the regression line, right? So this is the square root of the mean squared error.
Yes.
And you have to look at this p-value. It's a null hypothesis test, so it means that it's like it's a null hypothesis when all the coefficient and the intercept simultaneously zero. That's what it is. You have to look at this one, and you want to look at this column here to determine which variables are significant predictors, and you want to look at the residuals too. So residuals is a difference between the predicted value and the fitted value, right? The actual value. So you want to look at the maximum difference, and you want to look, see this is a minimum, the maximum difference, right? And you want to look at the median. See, this is a 5-number theory, 5-number summary, sorry, for this, right? So, and you want to look at the R squared, so there are a lot of things to look at. And we are not doing the confusion matrix for the prediction. So this is something important to remember as well. And see, here is a list of your coefficients, right? And you've got the formula. And see this, basically, when you have only one variable, then the t-test and the f-test results are going to be equivalent, right?
Yes.
And another thing what I was doing here, when I was building the reduced model, I used the backwards method. So I was stripping off, I was stripping the variable one at a time. Alternatively, there is also the forward, right? So I did not do that, I just did the backwards, right?
Correct.
So basically, the p-value is the probability of obtaining the value of the t-test statistic as observed, right, or more extreme. Yeah. As observed the null hypothesis, right?
Yes.
Exactly. And it's probably also spelled out in the exercise handout that you received in a assignment, right? If you look at the assignment, you see the Word document, but there is also the optional or I would like to call it recommended rather exercise for logistic regression and for naive Bayes. At least do the one that you're using for the assignment 3. Is it 3 or 2? 2. That's 2, right? Yeah. So yeah, I mean, I like questions. It helps everyone. But whenever we have a class, if for any reason you cannot make it, right? If for any reason you're unable to make it, what you could do is that send the questions that you would like to be addressed during the WebEx. That would help you and help other students too. And this is an option that other students who could not make it today, they had that option. I should have announced it more clearly. They could send me the questions and then I can address them. Right? Yeah. But for the WebEx, what time do you think works better? Well, it's a good question, right?
It depends on.
Last week?
No, earlier in the week, not Saturday or Sunday.
Okay, that's what I'm going to do.
I need the information earlier.
Right, that's what we're going to do. This time I thought focusing more like on logistic regression because this is for the assignment. Here are the methods that you use in exercise and assignment are not the same, and assignment has a higher value. So I wanted to make sure that you have a chance to read. But so basically, Thursday night is good, right? Thursday night. Okay. I'll see what we can do. Yeah.
Yeah, earlier in the week, beginning of the week would be better actually.
Or middle. Yeah, because I want to make sure that people read. It's not a substitute for reading, but it's a supplement. Okay. I'll do that. Yes.
Cool.
Okay. Yeah, let's see if you have more questions because I love questions. It helps everyone, right? And I realize it's a lot of packages, but install only what you use, right? You don't want to. And also, speaking of packages, once in a while you want to do this. You go to packages and update. You want to have latest and greatest. Yeah. At the end of this month, or early next month, a new version of R is going to be coming. Well, it's going to be a patch. It's not going to be totally new, but it will be a little patch of this version. 3.4.1. Yeah. So something to look for. Yeah. So anything else you would like me to go over? Any other questions on these 3 methods? And I put comments to make sure that it helps you understand what I did. So the script that you'll get after this, it's going to have comments in it. Right? So let's see. Any more questions? Do we get bonus points? I'm making it up. Do we get bonus points? Well, not explicitly, but see, this, by attending this, you learn more than your classmates, right?
That's correct.
Yeah.
That's
true. And it is free.
That's why we're here.
Well, because it's taken into account when you pay for the class, right? Huh?
Yeah.
So yeah. So let's see what other questions you may have. That's an opportunity. Well, I guess if there are no more questions, then we're gonna call it, right? And as soon as I get the link, as soon as I get the recording, I'll convert it to YouTube, and I'm gonna post all of the files, right?
Sure. Thank you.
Elena.
Oh, you're the most welcome. So let me stop sharing my screen, and I have.
Thank you, Elena.
Okay. Thank you guys for attending. I appreciate it. Okay. Bye.
Have a good day, rest of the day.
Thank you. You also. And good luck.
Thank you.